Tá bom? Okay. Good afternoon, everyone. Today we are continue the mini course and about the resolvent and the proximal point method. First, we begin with recalling some things we have discussed in the last class about the average operator. We suppose the sequence xk is generated by the fixed point iteration t of xk, and here t is what we call averaged operator. Okay, it could be theta averaged operator, which means t can be equals to theta multiply identity plus 1 minus theta multiply some operator s, and here s is called non-expansive operator, which satisfying sx minus sy is less than the norm of x minus y. The reason why we need to study average operator, because if you do the fixed point iteration with the non-expansive operator, then it may diverge, imagine the rotation, 90-degree rotation, okay? So if we deal with theta averaged operator for the fixed point iteration, where theta belongs to 0 and 1, for any initial point belongs to the whole space, then we can prove that the sequence xk approaches a solution x star which belongs to the fixed point of operator t, and actually the fixed point side of the operator t equals to the fixed point side of the non-expansive operator s. So as long as you have a very interesting operator s, you want to find the fixed point of operator s, but you cannot use it directly in the fixed point iteration. You can use the corresponding or some theta averaged operator. This is what we proved last class, which is very important in the whole mini course, which can be used to prove like the gradient descent method and also the following the convergence of a proximal point method. Okay, so this is the theorem 1 in the last class. Next, we discussed the proximate point method. Proximal point method, which is solving a maximum inclusion problem, which is we found to find ax such that 0 belongs to the ax. If we say this problem, we are interested in the maximum monotone inclusion problem, which means the operator A here is called, I write it here, it's called maximal monotone. Okay, and if it is a maximal monotone operator, we can use the iteration which defend in this way, txk, which equals to identity plus some positive number plus the operator A, the inverse of xk. Okay, this is what we call the proximal point method. And this part, this operator, we define as the resolvent of A. Okay, why does the proximal point method converge? The next theorem established the convergence result and also the relation of maximal monotone operator and the averaged operator. Okay, here I write it as here, maximal monotone. Okay, so the theorem says that if the operator A is maximal monotone, then we know that the result, actually if it is monotone, then we can see that the resultant of A is what we call formally non-expansive. Okay. Furthermore, if the operator A is maximal monotone, we can also prove that we have two conclusions actually. First is the resultant, of course, is firmly non-expansiveness, and the domain of the resultant of operator A is the whole space. Okay, this part, this conclusion, we also call it Minty surjective theorem, which is also very important in the maximum monotone theorems. Okay, so today we will begin from the conclusions, these two conclusions. Okay. So this is the maximum monotone conclusion problems, and we have the proximate point method. It's a fixed point iteration with using the operator, the resultant of the maximum monotone operator A. Okay. The motivation, we have two motivations. The first is the resultant is averaged operator. Okay. Since it is average, actually it's 1/2 averaged because it's firmly non-expansiveness. And then we can see that the resultant is single valued, which means it is well defined. The algorithm is well defined. It's sorry. So the resultant is defined in this way. Okay, the GA equals to the inverse of identity minus A, and the reflect operator here is defined 2 times the resultant minus I. Here you can think about the reflection. How do we define the reflection in the Rn? We can define the reflection of point x with respect to a closed convex set A equals to the 2 times the projection of x on A minus the minus x. Okay. Also, you can write it as 2pa minus identity of x. So this is a kind of a generalization of the reflection on a convex closed set. Okay, so the theorem 1 in this slide is what I mentioned before. Okay, the first hold automatically because the definition of the resultant, and the second hold because A is monotone, and the third hold because A is maximal monotone. We will prove the second conclusion first. Before we prove that, we need some facts that we have mentioned in the first class. We see that the following facts are equivalent. T is firmly non-expansive. T is 1/2 average. Actually, this is somehow the definition of, not definition, but they are equivalent. And the 2t minus I, actually it's the reflection of operator T is non-expansive. So if we want to prove T is firmly non-expansive, we can prove the second one or the third one. So if the idea of the proof, theorem 1 is like this. Since we want to prove the resultant is firmly non-expansive, okay, we use this equivalent statement. It is equivalent to prove we can use the reflection of A, which equals to 2 times the resultant of A minus identity. we only need to prove this is non-expansive. Okay. So we prove the first part of this theorem. We assume that x, u, and y actually belongs to the operator. When we say a pair belongs to the operator here, we means it belongs to the graph of this operator, okay? So we can get x belongs to u plus au, and y belongs to v plus av. I'll explain a little bit here. It's by definition. So if x, u belongs to the resolvent of A, of A, it is equivalent to say this pair x, u belongs to the graph of the resolvent. So it is to say, what is the definition of here? The definition is I plus A inverse. Okay, so we see that x, we see that u belongs to I plus A inverse x. Okay, so actually, since this is single valued, we can use equal here. Okay, so it is equivalent to say x belongs to I plus A u here. Be careful. Here you cannot use equal anymore because A is a maximum monotone plus I. We cannot determine this operator is single valued. We need to be careful about that. So we have x belongs to u plus A u. Okay, so you can get the same similar result. Y belongs to v plus av. Okay, and since A is maximum monotone, of course A is monotone. So we have this. Okay, and this is just by the definition of maximum monotonicity and these two relations. Okay, so next we have this inequality. Okay, because the ideas to prove the resolvent is firmly non-expansiveness. It's equivalent to say the resolvent, the reflection of A, which 2 times the resolvent minus I is non-expansive. So what we do? What is non-expansive? The definition of non-expansive is here. Okay, here is the definition of non-expansive. So we analysis R A reflection of A x minus reflection of y. We want to check whether it's less than x minus y, the norm. Okay, if it holds, we have the we can prove the reflection of A is non-expansive. So we expand it by the definition. Okay, so here it's just the two resolvent of A x minus x and minus 2 the resolvent A of y minus y. Okay, and because you have the you have what okay, so from here we can see that x minus u also belongs to the au. Okay, so we can use the sorry about that. We use this u equals to the resolvent of A. So here we have 2u minus x minus 2. This is v minus y. Okay, then what we do is we expand this term. Okay, we expand this term. Of course, we have square here. Okay, if this has a square, it is equivalent. So we expand the square Then we get the inequality, which in this slide, okay, this inequality. Why we expand this? Because we want to prove the reflection is non-expansive. So we expand this, we get this identity, okay, x minus y squared, and we have the minus 4 times this term. And we know this term is greater than 0, so minus is less than 0, so we get this, this quantity is less than or equal to x minus y squared. So we proved RA is non-expansive. So we can write the resolvent of GA as the convex combination of I with the reflection, and the convex coefficient is 1 over 2. So it's 1 over 2 average because RA is non-expansive. So we finished the first part of the theorem. This theorem, okay, we proved if A is monotone, and then the resolvent is firmly non-expansive, which is 1 over 2 average. Next, we will prove the second part. Actually, it's the third part because I call it the second part because the first one hold automatically. Okay. So next we go to the Minty-surjective theorem. The Minty-surjective theorem says that the domain of the resolvent is the whole space if A, operator A, is maximal monotone, which is quite important. For example, we can see a application first. Okay. So if we have an operator Z here, okay, and we want to prove the zero side of this maximal monotone operator A is closed and convex. If it is not closed and convex, we cannot. It is very difficult to analyze the convergence of the sequence generated by the proximal point operator. Okay, and yeah. This is true because of the resolvent has a full domain. Okay, so here, this is application of the Minty theorem in the direct application. Okay, let's go back to the Minty theory. Okay, so the techniques in the proof of Minty theories is like we analyze the result in a function which is called a representative function, which has because usually this function is like what we like CCP function, and we get conclusion about this representative function, and we make a conclusion about this function, then we derive this result to the corresponding operator or the original operator. So we need to establish the relation between the maximal monotone operator and its corresponding representative function. So the function is called Fitzpatrick function, which is noted by the FA. It is defined in the Rn times Rn, okay, because it has two variables, and it admits the infinity, okay, admits the infinity. So the definition is FAU equals to the inner product of XU minus the inf of this inner product, okay? Inf for any YV belongs to A, which means belongs to the graph of A. Since this UV, we can convert first this infinite to the soup, okay? And then since this XU has nothing to do with UV, so we can put this XU inside. So it is equivalent to say the Fitzpatrick function is defined by the soup in the pair of YV of this the sum of these three terms of inner product. We have some properties of these Fitzpatrick functions. Okay, if we assume the operator A is maximal monotone, then we say first this function is CCP. Okay, if f is CCP, we have a lot of good properties like since it's CCP, it is a subdifferential in the relative interior of the domain. Okay, and the subgradient of the CCP function is also maximal monotone. And the second is that the FAXU is greater than UV for any UV in the whole space. And it equals to XU for any UV belongs to A. So first we check the proof of this lemma 2. We have some remarks. So first, this is it's a representative function of A, and second is this function is convex extension. Okay, actually it's not only convex extension of the inner product from A to the whole space. Actually, you see, the extension is from A to the whole space, and also it is upper bound of the inner product. And if we analyzing the FA, which is a CCP function, and we can use, usually it's easier to analyze the operator directly. Okay, so here is a proof. We have two cases. First, we assume the XU belongs to A. Okay, the XU belongs to A because A is monotone. Okay, for any YU, we have this. We have this is greater than 0. Okay, because both the pair XU and pair YV belongs to A, and it can reach its minimum. Okay, when the XU at the point XU, when YV is just equals to XU. So if XU belongs to A, we have this identity. Second, we assume the XU not belongs to A. Here we need to use a maximality. Okay, since it is not belongs to A, so we can find a pair YV such that the monotone is not satisfied anymore. If it is satisfied, it will have a conflict with the assumption that XU not belongs to A. Okay, so we take the infinite both sides. We have the infinite of this is less than 0. Okay, so since it is less than 0, we can conclude FA is greater than XU by the definition of FA. Okay, I write the definition of FA here. The definition of FA, XU is equals to the inner product of XU minus the infinite YV belongs to A, and it's X minus Y, the inner product of U minus V. Okay, this is the definition of this Fitzpatrick function. Okay, so next we are going to prove the capital FA is a CCP function. Okay, we define the small f YV XU is equals to the sum of the sum of these three inner products without the soup. Okay, without the soup, because here the definition of the FA has it's also equals to the soup. YV belongs to A, and the inner product of Y u plus xv minus yv. Okay, it's different. So, since this function is closed, since this function, small f yv, is closed and convex for any y belongs to A, because it's just the sum of this kind of linear, the sum of inner product. So it's a function. It's closed, and how to say it is closed, because we can say the epigraph of this function is closed side. Then we can say the epigraph of the capital A is just the intersection for any yv in A. Actually, it's the epigraph of intersection of many epigraph of function f yv. For each yv is for each pair yv belongs to the set C. Okay, this is because this conclusion comes from the definition of the capital Fa is the sup of this the sum of these inner product. So we say the epigraph of the capital A is closed and convex, since it's an intersection of closed and convex sides. Okay, so we say that f is closed and convex function. Then we prove it is proper. Okay, proper means the function cannot approaches the negative infinity. Okay, so since we already proved that Fa, since by the definition, Fa is greater than any Fyv for any pair Yv belongs to the graph of A, and for any Yv, this is this pair, this function is a finite value. Okay, finite value. So we have Fa is greater than any negative infinity. On the other hand, we see that when for any xu belongs to A, because if you want to prove a function is proper, one is to say it cannot reach the negative infinity. Another is to say the function cannot be positive infinity everywhere. So we need to prove somewhere the function value is not positive infinity. So we say that here Fa xu is equal to xu. This we have proved before for any u y belongs to A. So this is finite, okay, because it's inner product of two vectors. So this is obviously less than positive infinity. So we say that f is proper because of these two parts. One part is to say it cannot reach the negative infinity. Another is to say it is not a positive infinity everywhere. Okay, so with this definition, with the definition and the property of this Fitzpatrick function, we are going to prove the Minty surjective theory, okay, with this function and the properties. Sorry. We need to go back. Okay, we prove the Minty theory. Let's recall the Minty theory. We say A is a maximal monotone operator. Then we say the range of the I plus identity A is the whole space, or it is equivalent to say the domain of the resolvent is the whole space. Okay, so the strategy to prove is we want to show first we want to actually we want to show for any u belongs to the Rn, we say that u belongs to the range. Okay, but before to conclude this, we first conclude that for 0, we prove that 0 belongs to the I plus identity of A for any maximal monotone operator. Then we can prove that since A is maximal monotone, if we have a minus shift outside B is still maximal monotone. Then we can see if the first is satisfied, then we can see that the 0 also belongs to the range of I minus B identity. So it is equivalent to say for any U belongs to the this should be Rn. For any U belongs to the Rn, we can see that U belongs to the range of the I plus the identity of I. So let's first to check whether 0 belongs to the range of this operator. The idea is we want to use the this representative function capital Fa, okay? Because this F is convex, so we can use the subgradient inequality. Before we use the subgradient inequality, we need to find which one is a subgradient, okay? So we first define the pair U, Y, V is the argmin of this function, okay? Since it's obviously this function is convex, so we can say that. I will write it here. We define Y, V equals to the argmin of F A X U plus X square U square for any X U belongs to the whole space. Okay, so we need to say that the optimal condition of this problem is the 0. Okay, okay, we'll write it as the 0 belongs to a subgradient of this function. Okay, so it is equivalent to say 0 belongs to actually we can use the identity of the subgradient of the convex function. So we have this equals to the subgradient of Fa x u and this should be y v and this should be y. This should be v. No. Sorry about that. Okay, so this is YV and plus the, actually here is the Y0 and 0V. Okay, so we have the 0 belongs to the gradient of A, Y, V plus the YV, and we put this on the right side, we minus this vector on both sides. We have minus y minus v belongs to the subgradient of a y v. Okay, this is how we get this relation here. Okay, it's just use the optimality condition of this convex function. So as long as we get this vector minus y minus v belongs to the subgradient of this Fitzpatrick function. So this vector is a subgradient. So we can use subgradient inequality, okay? For any uv in the whole space, we have this. You see, here is a subgradient, okay? Here is a subgradient. And this is the subgradient inequality, okay? And by the lemma 2, okay, by the lemma 2, for any uv in A, we have, actually, we have two parts, am I right? Let's go back to the lemma 2. We have two parts. First, for any x u v, for any x u or x u in the whole space, we have this inequality, and for any x u in A, we have this inequality. We use these two terms together, and we can get this term. Okay, for here, pay attention. For any x u belongs to A, not x u belongs to the whole space. So we have two inequality here. First is getting by the subgradient inequality of this representative function, and another is getting by the property of this FA function, Fitzpatrick function. So we plus this inequality together, we get this inequality for any x u belongs to A. We need to pay attention for x u belongs to A. So because this is greater than 0, so we have A is, since it is maximal monotone. So because, I write it here, explain a little bit here. First, we have this x plus y, and u plus x plus v. U plus y is greater than 0 because the square norm is greater than 0. So you can write this term as x minus v, u minus y is greater than 0. Okay, so because the A is maximal monotone operators, recall the definition of maximal monotone. It means we cannot find another monotone operator such that monotone operator S, that the graph of A is contained properly in the graph of S. So, which means this pair minus V minus Y belongs to the graph of A. This is because the maximality. Okay, so we have this pair minus Y minus V belongs to the operator graph of A. Okay, since this pair x u v is any pair in the graph of A, so this holds for any xu belongs to A. So we can take x equals to the inverse of V, and u equals to the inverse of y. So this inequality becomes 0. Okay, so this term becomes 0. Okay, this term becomes 0. I write the whole inequality here. So this is x plus v, y, u plus y is greater than y plus v square. Okay, and this coming. So we if we take x equals to the minus v and u equals to the minus y, what we can get these terms is 0. Okay, so we get 0 is greater than y plus v squared. So what does it mean? It means y should equals to the minus v. Okay, so if y is equals to the minus v, which because we already see that the minus says this conclusion. By the maximality, we already proved the minus v minus y belongs to the graph of A. And here we get another conclusion, y equals to the minus of v. And we use this conclusion in this relation. So we get what? Y minus y belongs to the graph of A. Okay? Y minus y. What does it mean? It means, we explain a little bit this relation. It means, sorry, I will write it here. This means the minus y belongs to a y, okay? And then we get 0 belongs to y minus ay. So we get 0 belongs to identity plus a y. So we get 0 belongs to the range of I plus a. Okay, so we have proved this result. Okay, then we use the surjectity we have explained here. Okay, the second step, since B is also a maximal monotone operator, as long as A is a maximal monotone operator, because U is just a vector, this kind of minus shift outside will preserve the maximal monotonicity. So it implies U belongs to the range of this operator for any U in the whole space. So we proved the surjective theory. Okay, we make a summary here. If A is maximal monotone, the range is the whole space. All the domain of the resolvent, always say the domain of the inverse of this operator is a whole space. Okay, so this is the Minty theorem. We go to immediately application of Minty surjective theory. We want to prove the 0 side of A is closed and convex when it is maximal monotone. Okay, first, we can prove that the 0 point side of A is the fixed point of the Minty theory. No, the resolvent. This is the idea why we can use the proximate point method to solve the maximal monotone inclusion problem. Okay, the reason is this very trivial explanation. So since we already proved that if A is maximal monotone, the GA is non-expansive. Not only non-expansive, but with the domain equals the whole space. So if we have a non-expansive operator and the whole domain, then we say that the fixed point of this operator JA is a closed and convex side. Then we can conclude immediately the 0 side of A is closed and convex. Okay, so this proof relies on the maximality of the domain of the resolvent is a whole space. we see some examples and properties of the resolvent. Okay, first, if A is a monotone and linear, okay, linear operator and represented by a symmetric matrix, then A has the eigenvalue of from 0 to the infinity, okay, and then the resolvent here has the eigenvalue between 0 and 1. And the reflection operator, okay, the definition is 2 times the resolvent minus I, which could be equals to the I minus I times the I minus plus A infinite inverse. And these two matrices are, you can change it in another direction, okay? And also the reflection operator of A has the eigenvalue between the -1 and 1. Okay, we do not prove it. You can check them very easily with the knowledge from the matrix analysis, okay? And we also have some resolvent identities. For example, if we have a maximal monotone operator A, we have a shift outside minus a shift inside, or minus shift, inverse reflection and inverse outside, then the operator B in these three cases are still maximal monotone, and the resolvent of B relies on the resolvent of A with just some modification, okay? You can check them very easily with the definition of resolvent. And okay, this is a very interesting result. It's called the inverse resolvent identity. The proof is not very trivial. You need to use some properties of the formally non-expansive operators. Okay, we just go to a special case when the alpha equals to 1. It is to say the resolvent of A plus the resolvent of the minus A is identity. Okay, identity. It says that if we know the formula, or if we know how do we calculate the resolvent of A, we know immediately how to calculate the resolvent of the inverse. And as a special case, if A is a CCP function, we have the Moreau identity, which is a proximal operator of F plus the proximal operator of the F star, which is a conjugate function, is equals to the X. We will see later what is a proximal F, okay? And we can see from this identity that these two operator has the same computational cost, okay? And another is if A is maximal monotone and also single valued, we can have this inequality. It's a kind of a decomposition of the reflection operator, okay? Of the RA equals to the identity minus IA is equals multiplies the inverse of this. We need to be careful. Usually, this operator I minus alpha A or I plus A is not single valued, even if A is maximal monotone. But the inverse is single valued. So in the proof, we use A is single valued in the second line here. We need to use this operator here. It's the single valued. You can check it by yourself later. It's a very important result in many analysis of the splitting method. We will use this result later in when we talk about the splitting method. Okay, next is if A is not necessarily single valued, we can also have this result. We do not take too much time to prove this. It's just by the definition, okay? Next, we want to talk about if we want to use the proximate point method for convex optimization problems, especially for the unconstrained optimization problem. Now we consider the unconstrained problem. We minimize a function, CCP function, f, in the whole space without any constraints. Okay, the optimality condition is 0 belongs to the subdifferential of x, which is equivalent to Cx is a fixed point of the inverse of this operator. Actually, it's the resolvent of the differential of f. Okay, just here is by the definition of the resolvent. And we can conclude the convergence immediately. First, since f is a CCP function, I write the analysis here very easily. F is CCP. So we can immediately conclude that the gradient of f is maximal monotone. Okay, so these problems becomes a maximal monotone inclusion problems. So this is maximal monotone inclusion problem. Obviously, we can use what we have discussed before, just now, the proximal point method. So we can use xk plus 1 equals to the resolvent of the operator is the subgradient of f xk. Okay, so this is just I plus lambda, the subgradient of f inverse xk. So this iteration is the proximal point method for the unconstrained optimization problems. We continue here. Since this is CCP, this is the subgradient is maximal monotone. We immediately get that the resolvent of subgradient of f is averaged operator. Okay, it's averaged operator. So we say that the sequence generated by this iteration converge. Xk plus 1 will converge. I write it on the other side. So we immediately get that the sequence generated by this iteration, xk, converge to some x star, which belongs to the fixed point of the resolvent of the subgradient of f. Okay, and we have proved that the subgradient of f, the fixed point side of the resolvent of subgradient. Sorry, I see it a little confused. This is equal to, this is equivalent to say that 0 belongs to the subgradient of, okay, which is equivalent to say x star is the argmin of f. Okay, we can conclude it immediately by the convergence we have talked before. And the next problem is we want to know what is exactly, or do we have a closed formula of this resolvent when the operator is a subgradient of a CCP function? The answer is yes, we have a closed formula. So next we want to explain or say why the resolvent of the subgradient f is just the proximal operator of f. The proximal operator is defined in this, okay? So we will prove this. It's just by the definition and the optimality of condition of optimization problems. Okay, so first we want to prove the resolvent lambda of lambda, the subgradient, is equals to a proximal operator of lambda f. Okay, so we assume Z belongs to the identity plus the resolvent of x. Be careful. We can write equal here because the resolvent is single valued. Okay, so by the definition of this, we can write x belongs to the I plus alpha, the subgradient f of z. But we cannot write equals here because this operator, even if what I have explained before, even this is maximum monotone, but it cannot imply that it is single valued. So this is equivalent to say x belongs to z plus alpha, the subgradient of z. So we have, it is equivalent to say 0 belongs to z minus x plus the subgradient alpha, subgradient of z. We use the subgradient identity here, so we can conclude that. So this is equivalent to say 0 belongs to the partial of the whole function, okay? The partial of whole function with respect to z. So it is to say it is partial z minus x plus fz. So we can define this function, this part, as a function h, okay? hz. So what does it mean? What does this mean? It means 0 belongs to the subgradient of hz. So it means z is the minimizer of this function, okay? So we can conclude that z belongs to argmin of this is a subgradient of hz, okay? So what is hz? Hz should be 1 over 2 z minus x squared plus fz. Okay. So it is equivalent to say z is the argmin with respect to z of this function. So this is a definition of the proximal operator with respect to it should has alpha here, okay? Alpha f of x. Okay, so we finish the proof here. So if we want to calculate the resolvent of a subgradient function, the resolvent is immediately equals to the proximal operator of f, which just the definition is here. We have several kind of interpretations of what does this proximal operator means. Okay, so we make a summation here. The proximal point iteration, the proximal point method for the unconstrained problems is just xk is just equivalent to say xk plus 1 equals to, we use the proximal operator here, okay? And if the function f is CCP function has a minimizer, then we say the xk converts to the set of minimizer, one of the minimizer, and the fxk converts to the optimal value. Actually, this comes from the theory, convergence theory of the proximal point method. But if we do not want to use the fixed alpha here, if we change the alpha equals to alpha k, and if this alpha k is not summable, then the convergence is also guaranteed. This is the first interpretation of the proximal operator, okay? But I will not explain it to take too much time. If we define the infinite convolution of a CCP function, and f and g, it equals to this notation by f square g of v, okay, it's the infinite of this. And then with this infinite convolution, we can define the Moreau envelope, or the Moreau-Uceda regularization. It's m lambda f. It equals just this, the infinite convolution of the function f and the norm square. Okay, so it is equivalent to say the Moreau envelope equals to the infinite in x of this function. Actually, this is very similar to the proximal operator, right? We say the proximal operator is defined by the argmin but argmin in variable z or variable z. But here is defined by the infinite of the function value. So the relationship is, before we go to the relation, we need to say a little bit about this kind of Moreau envelope, okay? Actually, this Moreau envelope is called Moreau-Uceda regularization. It's a kind of smooth approximation of the original function f. We see that if C is a CCP function, but CCP function may be not differentiable, okay, maybe not differentiable, then but the Moreau envelope is smooth and has the full domain and the domain is a full space, even if the f is not differentiable. And this Moreau envelope has the same minimizer with f. You can check it very easily, okay? And example is, we check this absolute value function f. Of course, it's a CCP function. It's a CC closed and convex because the epigraph is closed and convex. It's a proper because it will not reach the negative infinity and it's has at least somewhere finite, okay? And its Moreau envelope is you can derive it by the definition, okay? Is the Moreau envelope of this function is this Huber function. And we can see this function is differentiable everywhere, okay, and has a full domain. So since it is differentiable, you can use the methods you have studied before for the smooth problems, like the gradient descent method, okay? And we can, the relation is, if we take the, when the point x equals to the proximal operator of f, then the Moreau function, because the Moreau has the infinite here, but if the point is just the proximal operator, we do not have, it reaches its infinite, okay? And in addition, we can calculate the gradient here, okay? Gradient of the Moreau envelope. Because it's smooth, we can calculate the gradient, and we can rewrite it, and we see the proximal operator of f is just the x minus lambda, the gradient of the Moreau envelope, the grade f, grade m. It's a kind of a gradient step size, gradient descent step for the function m, capital M, okay? And some other interpretations. If f is twice differentiable, okay, we assume the Hessian is positive definite. When lambda is small enough, we can say that this comes from the idea of the Taylor expansion, okay? The proximal operator of f is just the gradient descent step with a small arrow here, okay? And if f is differentiable, it's a first order approximation is this. It's the first order approximation, and then we calculate the proximal operator of this first order approximation. It's just the same as the gradient descent of the function f, okay, of the function f. And if it is twice differentiable, we can have the second order approximation. It has the function value, the first order approximation, and second order approximation. And if we calculate the proximal operator of this second order approximation, the computation is not difficult. You can check it very easily. We can have this closed formula, okay? If the lambda is infinity, it's just the Newton method, okay? If lambda approaches infinity, it's just the inverse of the Hessian of f. So, but if the lambda is small, very small, even if the Hessian is not positive definite, with this multiplication here, this matrix, the Hessian plus 1 over lambda plus identity can be positive definite because of these positive terms here, okay? So it is the Liebenberg Markout update or modified Hessian-Newton update. So for the proximal operator has several interpretations. Anyway, it has a relation with the gradient descent step. Okay, another interesting example is if say is a non-empty, closed, and convex site. We give a conclusion here. We recall conclusion. If C is closed and convex, as defined there, then the indicator function of C, if we calculate the subgradient, is just the normal cone of C, okay? And this function is CCP. And this is maximal monotone operator, okay? This is what we have discussed before. So we can get it very easily. Because this NC, the normal cone operator is maximal monotone, we can calculate the resolvent is well defined. So the resolvent of the normal cone operator is just the proximal operator of the indicator function, and it's just equals to the projection operators. It's very useful for conclusion in many analyses for the splitting method. Okay, so we can see that the resolvent is a generalization of the projection operator, because projection is just a special case when the maximal monotone operator is the normal cone. Okay, so next we will talk about application of the method of multipliers. Actually, the Rockefeller has discussed this in his paper about the proximal point method in 1976. So it's a very interesting and important application. But before we go to the method, actually, not only this method, and also most of the splitting method, they are prime and a primal door method, which means we do not only care about the sequence of the primal variable xk, we also consider the door problems and the door variables and consider whether the door variable sequence can converge to the solution of the door problems. So because of this, we need to introduce a little bit about the duality. And in this slide, we discuss the duality in the sense of, in the perspective of the saddle function. Okay, so first we calculate, we introduce the saddle function. We say the f depend on Rn times Rn and permit the both negative infinity and positive infinity. We say this function Lxu is convex concave if f is convex in x when u is fixed, and concave for u when x is fixed. Okay, and actually we have many examples. The first is the simple example is here. Fxy is x squared minus y squared. For fixed y, it's convex for x. For fixed x, it's concave for y, okay? Because it's the inverse, it's the minus concave, convex. And we also define the saddle point. X star u star is a saddle point of a function, the convex concave function L. If it satisfies this inequality, okay, it is greater than the x star for any u and is less than a fixed u for any x. Okay, so this is, we can say this red point is a saddle point of the function x squared minus g squared. Not only this, the Lagrangian, okay, defined by fx minus u, the inner product u with ax minus b, is also a convex concave function. Actually, this Lagrange is related to this problem, this primal problem. Or you can say it can generate this primal problem. We will mention it later. Because if x is convex, we fixed x, we fixed u, this is a convex function, okay? And if we fixed x for u, this is convex function because this is a linear function, a fan function for you, a fan function for you, okay? And also what we usually very frequently, the function we use very frequently is the augmented Lagrange, which is defined by plus or square terms, the penalty terms on the Lagrange function, okay? So we have some conclusion here. Both Lagrangian and the augmented Lagrange are convex concave functions, concave convex saddle functions. If xu is a saddle point of L, then it is equivalent to say, or if and only if it is a saddle function for the augmented Lagrangian. Because of this, sometimes we can use the augmented Lagrangian to establish the duality, and it has better performance, or it can gives you a better algorithms. We will see this in the later slide. If we use the Lagrangian, we get a primal door algorithms. If we use the augmented Lagrangian to establish the door or the primal door problems, we get a better algorithms. Okay, so first we forget about the Lagrangian function. We assume that the capital L is just a convex concave function. From this convex concave function, we can define the primal problems. First, we calculate the sup in U of function Lxu, and then we minimize in X. So this is what we call primal problems. Then we define the door problems, which is generated by first we take infinite in X of L, then we take the maximum of in U of this infinite. Okay, so as long as you have a saddle function, you can define these two problems as a duality. But it is hard to say whether the optimal value of these two problems are equal or no. But we can have some weaker conclusions, which we call weaker dualities, no matter whether the capital L is Lagrangian or augmented Lagrangian or whatever. Actually, the strategy of how do we use the duality to solve the problems is to choose a good saddle function L. You can see it in the later slide. Okay, so first, we go back to the Lagrangian. Okay, so this is a Lagrangian. If we maximums this part in U and minimize in X, with some calculations we get this problem. This is the primal problem for us. It's if X is convex, it's the convex linear constraint problems. And if we take the infinite of this part in X, we get this part. We get this minus the f star, which is conjugate function, and minus this term. This is how we just take the infinite in X of this part, and then we maximum this infinite, which is this door problem max in U. Okay. If this the feasibility set intersect with the domain of F is not empty, then we say the strong duality holds. What is strong duality? Which means the D star, which is the optimal value of the door problem, equals to the optimal value of the primal problems. Actually, this kind of regular condition, which can make the strongly duality holds, is what we call the constraint qualification. We will give an example of this kind of constraint qualification, which is a later condition in the later slides. Okay. First, we want to analyze a weaker result. If we do not assume there exists this kind of regularity conditions for the strongly duality, what can we get? We can get the D star, the duality, the optimal value of the door problems is less than the optimal value of the primal problems. Okay, for any x u in the whole space, okay, for the whole space we have, first we have this. This is just with as the definition of inf. Okay, we just take the inf in x for the this saddle function. So this is less than the for any x, okay, for any u. Okay, from the first inequality, we take the soup in u on both sides, okay, because the soup preserves the inequality here. So we have the soup in u if x L is less than the soup u L. Pay attention. Be careful. After this, in this inequality, the left side is just a number. Okay, it's just a fixed number. So we can take the infinite in x again on both sides. Because this is a fixed number, if we take the infinite in x, it doesn't matter. So we have, from this inequality, we take both infinite on both sides. So this inequality still holds. And remember the definition of the primal problems. I write it here to make it clear. If we have a L, X, U, which is convex, concave function. Concave for X, convex for U, okay? So the door problems is defined by, first we take the soup in U of L, X, U, and then we take the minimize or infinite, whatever, in X. Then we write the door problems. First we take the infinite of X in X of the function L, X, U. Then we take the maximum of in U of this part, okay? So the optimal value of the primal problems defined by the P star, and this is D star. Okay, then we conclude from the analysis here, the D star is less than the P star. Okay, this is what we call the weaker duality, which doesn't require any constraint qualification. Okay, for any convex concave function, we have this property. Strong duality holds often, but not always, in the convex optimization, the regularization conditions which ensures the strong duality are called the constraint qualification, which I mentioned before. Actually, next we will introduce a definition called total duality, which is come from the book I mentioned in the last slide as a reference, Large-Scale Convex Optimization, which is a relative new book, which is a very nice book, and I take a lot of materials from this book, including this definition. So what is total duality? Total duality means the primal solution exists, the P star, okay? The door solution exists, D star, and the strong duality holds, P star equals D star, okay? And we can check that if L has a saddle point, then the duality holds. It's also another kind of statement of the classical slate point theorem, okay? So why we should mention about this total duality? Because if total duality holds, solving the primal and Doric optimization problems is equivalent to find a saddle point of the convex concave function L. If you have a good method to solving the saddle point problems, it's better to solve the saddle point problems instead of the optimization problems. We will see later, the total duality is a kind of regularity condition that ensures the primal Dor methods converge, okay? Because as I mentioned before, many splitting methods are in this form. Also including the method we will mention in this slide, which is called the method of multipliers. Okay, so we prove this inclusion. Because of the time, we cannot finish the slide anymore. All of the things here. We finish this this slide in the last. We assume that L has a saddle point, okay? If L is a saddle point, what is a saddle point? The saddle point of L is that x star u star is less than the L x u star and is less than the L x star u. Okay, so this is the definition of the saddle point. So first, we see that if we fix the u star here, okay, we fix the u star, the L x star u star is just the inf in x of this function. It because of this inequality. This inequality, okay? If we fix the u here, then we can have the infinite in x, L, x, u star is just equals to the x star, u star. It because the definition of saddle point. And we take the sup of this function because u star is just is a fixed vector. We take the sup in u for any u. This sup should be greater than this part. Actually, we regard this as a new function, okay, with respect to u. So if we take the sup for this function in u, we have this sup in u in x, L is greater than this original one. And this is the optimal value of the Dor problems. And we already proved because of the weak duality. What is weak duality? Let's go back a little bit. Weak duality says the D star is less than the P star without any constraint qualification. So we use the weak duality here. We get this D star is less than the P star, and the P star is just the inf in x, sup in u, L x u, and this is less than for any fixed is less than for any for a fixed x star, because here you take the infinite of x for any x. If we take any x, for example, we take x equals to x star, it should be greater than the infinite, okay? So we take this as less than the sup x x star u, okay? So then we can have it equals to the x star u star by the other part of the inequality. So later we have, since we proved this, the infinite sup L is equals to the sup of L for any x, okay, for any x. So the x star is just the solution of the primal problems, okay? The x star is a prime, because this is a primal problem. This is the solution of the primal problems. It reaches as a point of x star. And because of the similar argument, we can see that the u star is the dual solution. And we have the d star equals to the p star. So we have the strong duality. So we have, because if we have a saddle point, we prove that the x star is the primal solution exists, the dual solution exists, and the strong duality holds. So we have the total duality. Okay. Because of the time, we stop here and we just make a forecast for tomorrow for the next class. In the next class, we will discuss about the method of multipliers from two point of views. First, we analysis from minimizing the dual problems by using the proximal point method. Or it is equivalent to say we use the resolvent. We can get the method of multipliers. Another ways we can use the another perspective of method of multipliers. We can use since the dual problems of the augmented Lagrangian, this dual problems is always convex optimization. So we can use the subgradient method, okay? If we use the subgradient method for these dual problems, we can also get the same method, which exactly the method of the multipliers. So next class, we will give two ways to get the method of multipliers, and also compared with another dual, primal dual method, which is called the dual ascent method. Okay, this is what we want to discuss today. Thank you. Obrigado.